All right, now we're going to talk about LLSE and vector estimation. We're going to define the acronym LLSE pretty soon, but the main thing you need to know about it is that it just means linear estimation. All right, so remember we introduced this framework for scalar estimation theory in the previous video. Okay, so just to review that, there's going to be an unobserved random variable that we were calling x and an observed random variable, and we were calling that y. And our job was to come up with an estimation rule, x hat of y. So this is a function that takes in y, predicts the value of x using only y. And in this specific chapter, we're interested in measuring the quality of prediction using mean squared error. There are other ways you could assess your performance, but we just stuck with this one particular metric, which takes x, subtracts the estimate, x hat of y, so that's the error, the residual, squares it, and then takes the average. Okay, so we already learned that the optimal performance is actually attained by the minimum mean squared error estimator. Okay, and that was abbreviated as MMSE. So the MMSE estimator, we also learned that that optimal estimator is just a conditional expectation. So I just take x hat of MMSE to be the conditional expectation of x given y. But the problem is this can be a pretty challenging thing to determine. Maybe that just means I have to compute some integrals, but in general, this is a hard thing to do, and it's often a nonlinear function of y. So let's just ask the following question. What's the best possible linear estimator, meaning an estimator of the form x hat of y is equal to ay plus b? So some linear scaling of y plus an offset b, and we're going to call this a linear estimator. Technically, it's affine because I have the shift b, but we'll just call it linear for now. And that's the convention. Okay, it turns out that the linear least squares error estimator, okay, and so this is kind of a cute change of terminology. So before we were calling things mean squared error, and here it's linear least squares error. And the reason people do this is just so you get two L's for linear instead of two M's for minimum mean squared error. And so that's just a notational convention, but maybe if it's something that you forget about, you might get confused. Just remember, LLSE is linear, best linear, and MMSE is the best. Okay, so this estimator is x hat LLSE of y. This is going to give us the smallest possible mean squared error among all possible choices of linear estimators. Okay, and so the way that we write this is the mean of x plus the correlation coefficient, and then we normalize out the variances, and for y, we pre-subtract the mean of y. So just to look at this from a different perspective, add in the mean of x, multiply by the covariance of xy, divide by the variance of y, y minus its mean. So what we're doing with y is we are removing its mean to start, right? Then scaling it so it's on the same scale as how predictive it is for x. So that's covariance xy divided by variance y. And then we're adding in the mean of x. All right, we're not going to show why that's the case. We're also not going to show what the exact derivation is for this, but it turns out the mean squared error is the variance of x times 1 minus the correlation coefficient squared. And another way of writing the same thing is the variance of x minus the covariance squared over the variance of y. So those are some nice formulas that can simplify a lot of calculations. You can look at your lecture notes to see why those are true, but we're just going to take them for granted. Okay, so remember at the end of the last video, we showed some formulas for the MMSE estimator for jointly Gaussian x and y, and it turns out that those are exactly the same as the LLSE formulas above. And that's because for jointly Gaussian x and y, the optimal estimator happens to have a linear form, so it just will lock into this form on its own. In general, that's not true. So if in general you want to use a linear estimator, you might lose some performance, but the form of it is the same as the form of a Gaussian MMSE estimator. All right, and the important thing to note is the reason we often use this is that it's often a lot simpler to figure out how to do this in practice, right? Because I don't need to know the joint PDF. I don't need a good model for the joint PDF or the conditional PDF. I just need first and second order statistics. So I just need to determine what I think the means are, what I think the variances are, what I think the covariance is, and then I'm done. I can just apply the LLSE estimator from there. But maybe I'm losing something. What are its properties? Well, it has very similar properties to the MMSE estimator. Let's just review. So the LLSE estimator, it turns out that it's also going to be unbiased, meaning that if I average this estimator, I get the average of x, which is good. So it, on average, is getting the right value. Why is that true? Well, just plug in the form of the LLSE estimator, take the average. So I have mean of x plus covariance of xy over variance of y times y minus its mean. Okay, so let's push the expectation in and see what we get. By linearity of expectation, the only thing that's really random here is y. So it's going to get converted to e of y minus e of y. That's going to be 0. I'm just left with e of x. So it makes sense. The other property is that the error of the LLSE estimator is going to be orthogonal to any linear function ay plus b of the observation. Okay, so not to any function. Any function was for MMSE, because for MMSE you're allowed to do anything, and then you'll end up being orthogonal to any function. Here you're only allowed to use linear functions for LLSE, so it makes sense that you're only orthogonal to linear functions. Mathematically, what this means is the error, x minus x hat, times a linear function on average is 0. And you can see the lecture notes for, some reasoning for why this holds. And it turns out, and we don't really need to do this because, as I said, we don't need to derive the LLSE estimator, but if you wanted to do it, one way you could do it is first show that it needs to be unbiased and orthogonal, so get these two properties, and then set these up as a system of linear equations for what you need for A and B, and then just solve those, and you'll get the form of the estimator we had before. Okay, so that's just a little side note if that's the way you wanted to derive it, but again, we're not deriving it here, so it doesn't matter too much. Let's do an example. Okay, in this example, we're going to have a joint PDF, okay, for x and y, and we're just going to say it's going to be constant, but the range is not going to be a rectangle, so they're not independent. So x is going to go between 0 and root y is going to go between 0 and 1. It's going to be 0 otherwise. Okay, so here is a depiction of the range. So this is the curve y equals x squared. And then, so that's that constraint. I also have a bound on y being less than 1, bound on x being greater than or equal to 0. So then I fill in this as the joint range. Okay, great. So to start out, what is the MMSE estimator going to be? Well, remember that the MMSE estimator is just the conditional expectation. So it's a function of y, and it's the conditional expectation of the thing I want x conditional on the value of y I observe. The formula for that is just the integral of x f of xy dx. And so I just need to figure out the range of integration. But first I actually need to work out the conditional PDF. That's the joint PDF divided by the marginal of the thing I'm conditioning on, right? And that's only true when that marginal is not 0, so I'm not dividing by 0. And again, I need to figure out the marginal of y. Okay, so finally the marginal of y, I integrate out from the joint PDF the variable I don't want, which is x. And so I see I need to set some integration range for x. And on this picture of the joint range, I see I go from 0 to root y for a fixed value of y. So my integral is just going to be x from 0 to root y times 3 halves. So I get 3 halves root y going from 0 to 1, because the whole range collapses onto the y-axis. So now I can divide here, 3 halves divided by 3 halves root y, and that's going to hold over the joint range. That's going to be my conditional PDF. It's not too bad, right? And so now I can come up above here, plug this in, I get x times 1 over root y dx, integrate from 0 to root y. So I really have a half x squared going from 0 to root y times 1 over root y. So it's going to be root y over 2. Let's plot that. Here it is. And this actually makes a lot of sense because this is actually a pretty simple example if you think about it. I have a constant height in my joint range, So the average should just be exactly in the middle for every single value of y. And you can see that's exactly what's happening. The outer limit on the right is root y, and the inner limit on the left is 0. So the halfway point for a given value of y will always be root y over 2, right? So that's kind of the average value. That's what I take for my MMSE estimator. It's nonlinear, but that's the best I can possibly do. What is the performance? Well, we need to evaluate the mean squared error, right? And we know that this, whatever number I get here, is the best possible performance I could have, but we're going to just get it so we can compare to the LLSE estimator in just a moment. So I take x minus the MMSE estimator for this value of y, square it, take the average. So this is an integral that's going to go from 0 to 1 for y, 0 to root y for x, and I plug in x minus root y over 2, the estimator, square it, 3 halves dx dy. We're not going to show this calculation here. You could do it on your own. It turns out to be 1 over 20, which is 0.05. Okay. What's the LLSE estimator? Well, again, I have the formula for that. So I'm going to write that down, and then I'm going to have to do some integrals along the way. Okay, so the LLSE estimator is going to be the mean of x plus the covariance of xy over the variance of y. And then it's going to be y minus its mean. And the other form works too that we wrote down with the correlation coefficient, but that actually involves one extra integral. So this one, you only have to do 5 integrals, whereas in that one, you would probably need to do one additional step past that. So we're just not going to use that form. We're going to use this form. So I'm going to get the mean of x. I'm going to integrate over some range, x times the joint PDF, which is 3 halves. The range is 0 to 1, 0 to root y. And that's going to hold for all of these because I'm integrating across the whole joint range. So I always use the same joint range. I just put in the thing that I want. So for the mean of y, I put in y. For y squared, which I'm going to need for the variance, I'm going to put in y squared. And again, it's going to be the same integral going from 0 to 1, 0 to root y for x. I'm going to do the same thing for e of xy. Same integral, but put in xy, 3 halves dx dy, right? And so this is pretty nice and symmetric. I can use a computer and just work out all these values. I'm not going to show you all the steps here. So I get 3/8, 3/5, 3/7, 1/4. So the variance is going to be the second moment minus the square of the mean. Okay, so it's going to be 3/7 minus 3/5 squared. It turns out that that is 12 over 175. For the covariance xy, I'm going to use the formula exy minus e of x times e of y. Okay, so that's going to turn out to be a fourth minus 3/8 times 3/5, which is 1 over 40. Okay, and so plugging all of this into my LLSE formula, I get 3/8 for the mean of x plus a 40th over 12 over 175 times y minus its mean, which is 3/5. Simplifying that a bit, I get 35 over 96y plus 5 over 32. Let's plot it. And we see that that gives me a line with an offset, and it's pretty close to an approximation of root y over 2 in the joint range. So this is actually a pretty good approximation, and it makes sense because, that seems to be the best linear fit I can come up with, just visually. Well, what is its performance? Well, I have to go through and use that formula that I gave you, right? You could write the integral down from scratch, but it's easier to just reuse some of these computations that we had. So we remember that this MMSE for the linear least squares error estimator is the variance of x minus the covariance of xy squared over the variance of y. So here, the only thing I need to do is figure out the variance of x, for which I need its second moment. So I'm just going to add one more integral here with x squared, 3 halves dx dy, range from 0,1 to 0 root y. That's going to be a fifth. Okay, so now I can plug all of this in. I have the second moment of x minus the square of the mean of x. That's going to be a fifth minus 3/8 squared, and that's going to be 19 over 320. So putting the whole thing together, 19 over 320 minus 1 over 40 squared, over 12 over 175, it's going to turn out to be 193 over 3840. And if you approximate that, you're going to get 0.0503. So it's actually really close to the 0.05 that we got for MMSE. So in this particular instance, as you can see from the illustration, the green line is a pretty good approximation of the blue curve, and the error is pretty much the same. You just give up a little bit. Okay, that's it for our example. Let's move on to vector estimation. So for vector estimation, I need to kind of develop my framework a little bit. So what's generally happening is I might actually observe more than one variable. Okay, so I might have more than one observed variable. Let's call them y1 up to ym. And maybe I also want to estimate more than one variable. Let's call those unobserved random variables x1 up to xn. Okay, and once you have so many variables, it's often convenient to organize all of these into vectors. So I have x vector, which is x1 through xn, and y vector, which is y1 through ym. And these might have different lengths. They don't have to be the same length. That's why I used n and m here. Okay, so I'm going to have a prior distribution as before. In the discrete case, that's going to be a joint PMF, and in the continuous case, a joint PDF, and I'm going to define it on this vector x. I have an observation model. That's how I observe y given x. I'm going to have a conditional PMF or a conditional PDF using the vectors, and an estimation rule, which puts out a vector after taking in a vector. And what that means is that I'm going to have a bunch of functions here, x1 hat up to xn hat, and each of those gets to look at the full vector of y. So it takes in y1 through ym, does what it wants to do, and it puts out an estimate for that particular value, x1 up to xn. So I have a vector valued function here, which consists of entries which are themselves functions, each trying to predict a different value of x. Okay, I can also think about the mean squared error, so that we call it MMSE. So that is just going to be the sum of the individual mean squared errors for each xi running from 1 to n. And you can write this using vector notation and an inner product. Okay, so this is a different way to write it. Sometimes that's more convenient. You take x vector minus the prediction of x vector with y vector, and then take the inner product of that with itself. So I get this error transpose times itself, and I take the average. Okay, so it turns out that the vector maximum likelihood, or ML, and maximum a posteriori, or MAP estimators, those are pretty simple to write down. So we actually write down basically the same thing that we had before, but this is an abstraction. And it could be quite challenging for us to compute these estimators for specific distributions. But let's put that aside. Let's write down the abstract formulas. So the ML estimator, x hat ML, is going to be in the discrete case, the argmax, and in the continuous case, the argmax. Discrete case, I have a conditional PMF, and I'm looking for the x vector that maximizes that. In the continuous case, I have a conditional PDF, and I'm looking for the x vector. The map case is the same, except I'm going to add in the prior. So in the discrete case, with both being discrete, I add in the prior of x, p of x vector, and in the continuous case, I add in the PDF of x, so PDF of x vector. And I do the same argmax. The vector MMSE, or minimum mean squared error estimator, also has a pretty compact formula, right? And the problem is, again, it's an abstraction, so maybe it's hard to compute this, but let's write down the abstraction. Okay, so this vector is going to be the conditional expectation of x vector given y vector's value. What does it mean to have the conditional expectation of a vector? Well, it means that I have a vector of conditional expectations for the individual entries, and I'm feeding in the values of y vector into each one. And if you think about it, y vector consists of y1 up to ym. So I'm giving you those m values organized as a vector. So you get all those m values, and now you have to figure out the average value of the variable you care about, x1 up to xn, condition on those values of y. Okay, and this vector notation is just a nice way to organize that. Okay, so what this means formally in the discrete case, so if I'm trying to take this expectation, what it means is I'm taking the average of the xi I care about, conditioned on the y1 up to ym that I have. And the continuous case, I'm taking that as an integral. Okay, so I just take this conditional expectation. The only difference is I'm conditioning on more things. And I have it either in the discrete or the continuous case. You can also show unbiasedness and orthogonality for the MMSE estimator in the vector case. We won't do that here. Okay, so we'll just leave that to your notes or to some later classes you might take. Okay, and these computations in ML, MAP, and MMSE in the vector case can get quite challenging. So what we often do is just restrict ourselves to linear estimators. Okay, so this is where linear estimation is really useful, is in the vector case. And we're going to use things which just look like a matrix A times a vector Y plus a vector B for some n by m matrix A and some length n column vector B. Okay, so that's the form of our estimator. I take in my y vector, multiply it by a matrix A that I get to pick, and then shift it by a fixed vector B, which I also get to pick. So the best possible choice for these this A and B turn out to come from the vector LLSE estimator. And so what I do is I just take the following form. So I have the mean of x, and I add this sigma xy. I'll say what that is in a moment. The inverse of sigma y. Remember, sigma y is the covariance matrix of y. Then y vector minus its mean vector. This is the form of the LLSE estimator. It's basically the same as the form of the scalar case, except now I've replaced the covariance with sigma xy, and I've replaced divide by the variance with the inverse of the covariance matrix of y. But otherwise, it basically looks the same. Okay, so let's just understand what these matrices are. So remember, this covariance matrix of y is just the following matrix. I take the outer product of y minus its mean times itself, okay, and I take the average. So I get this matrix filled up with these covariance terms, covariance y1, 1, covariance of y1, m, so that's the first row. And in the last row, I have ym, y1 up to ym, ym. So this is the covariance matrix, and I recognize that on the diagonal, these are just variances, right? So the covariance of a random variable with itself is just its variance. So what I'm left with is, what is this sigma xy? That turns out to be the cross covariance matrix, sigma xy, and we're going to define it here. What I'm going to do is take this outer product of x minus its mean times y minus its mean, okay? And so the way that looks is it's going to be the covariance of x1, y1 up to the covariance of xn, y1. So the first column holds y value fixed to y1, and then it varies x from x1 up to xn. So the index of the row determines the index of x, and then the index of the column determines the index of y. So here I have ym in this last column. Okay, and there are not going to be any variance terms here. It's going to be all covariances because now I'm always comparing an x term to a y term. So this is basically the same idea as we had in the covariance matrix case. So in the covariance matrix case, I'm generalizing the idea of variance to a covariance matrix of many random variables. Here I'm generalizing the idea of covariance between two things to a cross covariance matrix between many things organized into a vector. Okay, what are the properties? Well, they're basically the same as we had before. I'm just going to list them out for you. All right, well, the first one is going to be that the vector LLSE estimator is actually unbiased. Okay, so if I take its mean, I get the mean vector of x. I also have that the error of the vector LLSE estimator is going to be orthogonal to any linear function of the observation. Okay, so if I take the error, which is x minus x hat, multiply by any linear function and take the transpose so that the multiplication makes sense, I'll get the all zeros matrix. Okay, so this will actually spit out many, many terms if you actually take the time to write it out, which we're not going to do here, but all of those would be on average 0. Okay, so this is, again, probably a little bit outside our scope, but I'm just listing it so you see that it has the same kind of properties. And if this random vector x, y, so the stacking is jointly Gaussian, so everything is jointly Gaussian, then the MMSE and LLSE estimators are actually the same. So they're equal because jointly Gaussian you can always predict optimally with linear functions. And as before, the vector LLSE estimator can be derived directly from the unbiasedness and orthogonality properties. And that's actually a really convenient thing to have in hand. And you can see your lecture notes again for details. And this is actually maybe the preferred way to go about showing what the LLSE estimator really is in the vector case. Practically speaking, the real reason we really like this is we just need to learn the means and covariances in order to implement this. We don't need to learn this giant PDF, which might require a huge amount of data and a lot of sensitive fitting operations. We just need to do things like collect first and second order statistics, which, as we'll see, is actually a pretty easy thing to do, even with limited data. Okay, so we're just going to close out with an example. And we're going to do a vector example. And what we want to do here, all right, I'm going to go through every step. I want to estimate x from two noisy observations. And we're going to make things Gaussian here in a particular way. All right, so what that means is I'm going to have x, which is Gaussian with mean 0 and variance sigma squared of x. And z1 and z2 are going to be Gaussian, again with mean 0, but with variance sigma z squared. We're going to say that x, z1, and z2 are all independent of each other. And the thing that you're actually going to see here is going to be noisy versions of x. So y1, your observation is x plus z1. y2 is x plus z2. At this point, it's important to note that even though x, z1, and z2 are independent, that doesn't mean that x, y1, and y2 are independent. They're actually going to be quite dependent. We're going to use that. So what is the LLSE estimator in this case? Okay, and that'll actually turn out to be the MMSE estimator, but we're going to just do the LLSE estimator. So the LLSE estimator, we're going to take the mean vector of x, right? And in this case, it's important to know that x vector is really just x because there's just one value of x, so it's just a scalar. And the cross covariance matrix, which I've just written down here, just has x as a scalar. We'll see what that means in just a moment. Okay, so I'm going to write the form of the LLSE estimator. So this is the form that we had above. And I just need to work out these terms. We know the mean of x is 0 by definition. We know the mean of y by linearity of expectation is the mean of x plus the mean of z1, because that's how it's formed. And those are both 0, so it's also 0. We know the mean of y2 is also the mean of x plus the mean of z2. Again, these are all 0, so this is 0. So what I have to do is figure out the cross covariance matrix, which by definition is x minus its mean, times the transpose of y vector minus its mean vector, right? Take the average of that. Well, what does that look like? Well, since the means are all 0, this is just x times y vector transpose, which is just e of x y1 and then e of x y2. Okay, so even though the abstract formula looks pretty complicated, it actually just turns out to just be two terms sitting next to each other in a row in this example. And so what we'll get is e of x y1 is just e of x times x plus z1, because that's the definition of y1, which is e of x squared plus e of x z1. And this is going to be sigma x squared, because the variance of x in its second moment will be the same, because x has 0 mean. And the second term is going to be 0 because x and z1 are independent. So it just works out to be sigma x squared. And by symmetry, this is the same as e of x y2, because we would have done the same calculation, just changing z1 to z2. And we'll call that symmetry here. Okay. Well, I'm going to go through the same idea to get the covariance matrix of y, right? So I write that definition in terms of an outer product. What that's going to mean, since the means are 0 here, is that's the expectation of y vector times y vector transpose. And I can just organize that into a 2x2 matrix. It's the second one of y1, e of y1, y2, e of y1, y2, and then e of y2 squared, so the second moment of y2. Okay, so I just need to work out these terms. The second moment of y1 is just going to be the expectation of the square of x plus z1, right? So expanding out that square and applying linearity of expectation, I get e of x squared plus 2e of x z1 plus e of z1 squared. So that's great. I basically have all these terms. This middle one is 0 by independence, so I get sigma x squared plus sigma z squared, since these are both 0 mean. And this is going to be the same as e of y2 squared because of symmetry, and they basically just have z1 or z2. The e of y1, y2 term is going to end up being e of x plus z1, x plus z2. So I expand this out again, I'm going to get e of x squared plus e of x z1 plus e of x z2 plus e of z1 z2. And a lot of these terms are going to go away by independence. They're all going to be 0. And that's going to be sigma x squared. So I can write down these matrices now. The cross covariance matrix is just going to be sigma x squared, sigma x squared. The covariance matrix of y is going to be sigma x squared plus sigma z squared, then sigma x squared in the off diagonal, and then sigma x squared plus sigma z squared again in the bottom right. Okay, so we just showed those. So let's put everything together. Remember, I need to take the inverse of the covariance matrix of y, and recall from your linear algebra class that the inverse of a 2 by 2 matrix has this form. So if it's A, B, C, D inverse, I have 1 over the determinant, AD minus BC, and then I have D minus B minus C and A. So just writing that out in this particular case, I get 1 over 2 sigma x squared, sigma z squared, plus sigma z to the fourth. So you can just verify that those come from the same place. And then just reorder the diagonal and the off diagonal, which turns out not to matter by symmetry. I'm just basically adding a minus sign where I have minus b and minus c in that formula. And so then multiplying these two matrices together, it turns out that I have sigma x squared over 2 sigma x squared plus sigma z squared, and then sigma x squared over 2 sigma x squared plus sigma z squared. So it just turns out that's true. You can go through and verify that that's what that matrix multiplication winds up being. So putting all of this together, it's like writing the LLSE estimator as sigma x squared over 2 sigma x squared plus sigma z squared, 1, 1 as a row. So this is basically exactly this term that I wrote for sigma xy, sigma y inverse, but now I've just pulled that constant out and written the vector as 1, 1. I multiplied that by y vector, which is y1, y2. So I get this term sigma x squared over 2 sigma x squared plus sigma z squared, y1, y2. And this is basically what it's doing is it's averaging and scaling down due to noise. Okay, so we'll talk about what that means in just a moment. Let's first remind ourselves that since x and y are jointly Gaussian, right, then this also turns out to be the MMSE estimator. So this is really the best estimator I can come up with. And one other thing I can do, which is, we're not going to write it down here, but you could do it if you just spent a few minutes. You could also show that the ML estimator in this case, okay, for this particular example, is going to be x hat ML of y. It's just going to be the average of y1 and y2. So y1 plus y2 over 2. So I'm just averaging my two observations, which makes a lot of sense. The thing that's a little bit strange here is that if you look at the LLSE, or rather also MMSE estimator, I'm adding y1 and y2, and I'm dividing by something that's not quite 2, right? If that sigma z squared term was not there in the denominator, I would have sigma x squared over 2 sigma x squared, which would wind up being 1/2. But I'm dividing by a little more than that because I have sigma z squared. And what I'm basically saying is that I kind of think that my estimate is a little bit inflated because the noise has pushed me around. And so I want to back off a little bit from that. And what you can see is as sigma x squared increases relative to sigma z squared, you converge to something that looks like a pure average. And as it goes down, you basically just start downweighting it more and more, and basically trying to say that you don't really have a good estimator, and you kind of have to stay closer to the mean which is a reasonable guess if you don't really have any other information. That's it.